In this chapter, we're going to extend our study of calculus to include functions of several variables. Now, the models for those functions appear in a three-dimensional coordinate system. And let's talk about that a little bit. Let's develop the coordinate system a little bit, and then we'll get into the calculus concepts in the next section or two. You know, we start with in our previous discussions, we have a two-dimensional coordinate plane. And we have an x-axis and a y-axis, and they are perpendicular to one another. And they're arranged like this, where the x-axis is horizontal, the y-axis is vertical. Well, when we introduce a three-dimensional coordinate system, we need a third axis. And it's kind of logical to think that that third axis would go through like this. You see, just come out of the middle of the origin right here, and the 0 point on this number line would be at the origin of the original coordinate plane. Well, actually, we're going to rearrange it a little bit, and there is some convenience in this rearrangement, and we'll see that convenience later. But the way that it's arranged is like this, and notice the way that it's illustrated. And by the way, the illustrations in your textbook are outstanding. They are much better than I can do on the board, but let me take a shot at an arrangement right here. Notice the z-axis is going up here, the y-axis is to the right, and the x-axis is sort of coming at us. Now, to illustrate a number line that's coming at us, the positive values are coming at us, the negative values are on the other side of the board. But to illustrate the idea, we have to draw that x-axis somehow. So it's kind of drawn like this. Now, it puts the whole system into a kind of perspective which is not oriented toward right angles. And that's what makes the whole study a little bit difficult, a little bit challenging. But it's kind of like those little figures that you see sometimes in the newspaper where, you know, on Sundays you'll see these things in some of the magazine sections. You'll look at this figure. It's a figure that's drawn, and it looks like a repetitious kind of figure, and it's got color all over the place. And if you stare at the figure enough, things of certain patterns emerge, or there are figures nested within this, and you can't see them at the beginning. You have to stare at it a little bit. But then it becomes evident. Well, this is like that. When you study it a little bit, all of these ideas will become evident. But at any rate, the positive y values are to the right, and the negative values are to the left. The positive z values are above, and the negative values below, and the positive x values are in this direction, and the negative values out there. Now, we can draw the negative part of it, but I want to emphasize the positive idea right here. Now, in looking at the plane, in looking at the coordinate system, we can identify an xy plane. The xy plane, that's the plane containing the x-axis and the y-axis. And to draw that plane, now, if that x-axis is coming right at us, then the xy plane would be a flat surface like this. Now, to illustrate it, we have to draw it somehow, and there's a great drawing in your textbook once again, but we might draw something like this, you see, and then shade in here to try to see a flat surface. And in a similar way, we could talk about the xz plane, the plane involving x and z axes, and that plane would look like this. You see, it would kind of be out like this. And now it's coming toward us here a little bit, but we can't draw that. You see, we have to kind of draw it in perspective if we can. And then the YZ plane we can see very clearly because it is the plane of the chalkboard here, so it would be just this plane. Now, points in this coordinate system can be located using an ordered triplet of numbers. Now, that ordered triplet, like we have ordered pairs of numbers up here, the ordered triplet would be three numbers that describe three distances. The first distance is an x distance, a distance in the direction parallel with the x-axis, and this a y distance, a distance parallel with the y-axis, and this a z distance, a distance parallel with the z-axis. So using that idea, we can identify positions on the coordinate system. And we might do something like this. Now, these look kind of funny, but -2 for an x value. Now, x, the positive x's come out this way, so the negative x's would go in the other direction. You see, we might do that kind of thing. We might do the negatives for all of these axes. See, so an x of -2 might be, let's say, actually, if I want to draw about right here. And then 4 on the y-axis means to the right 4. Well, we're going to the right here. 1, 2, 3, 4. So it might be right here. And then 1 on the z-axis means let's go up 1. So the point would be illustrated right about here. And then for the point 3, negative 4, 2. 3 on the x-axis. 1, 2, 3. And then, actually I should draw these something like this for the perspective idea. But at any rate, 3 on the x-axis, negative 4 on y. That means to the left 4. 1, 2, 3, 4. And then up 2. 2 for the z, so up 2. So that point might be over here. Now, I think it's important the way that we sort of look at these values that are in the ordered triplet here. Now, you know when you have the coordinates of a point in our traditional coordinate plane, you can think of x values as being horizontal distances and y values as being vertical distances. Or you can think of x numbers, x values, as being distance from the y-axis. And that's kind of interesting. Now, let me just take a point here and show you what I'm talking about. Suppose I want the point 3,5, and it might be up here. The 3 can be thought of as distance from the distance from the y-axis. So it is a horizontal distance. It is the distance from the y-axis. The 5, a vertical distance, is the distance from the x-axis. Now, in a similar way, the numbers here can be thought of as distances from the various planes. So negative 2 is an x value, but it is the distance from the yz plane. Now, think about that a second. An x of negative 2, that means we went back, we went sort of behind our origin 2 units. Okay, but the yz plane is the plane of the chalkboard, so the negative 2 for x means 2 units, you see, from our yz plane. So each of these can be thought of that way, as a distance from a plane. That's a way of thinking about it. Well, let's develop further. Now, we're going to get some high mileage out of comparing comparable ideas in the three-dimensional coordinate system with ideas in the two-dimensional coordinate system. Let's talk about the distance formula. Now, let's go back to our two-dimensional coordinate plane. And if we want the distance from the point 3,2 to the point 7,5, here's how that idea was developed. And I know you may remember the distance formula, but here's how it's developed. And we need this development to develop the formula over here for the three-space situation. But it's based upon the Pythagorean theorem, and it works like this. We sort of make a little right triangle here, and if we call this distance A and this distance B, then this distance is C. And we know by the Pythagorean theorem that c squared is a squared plus b squared. So c then is the square root of a squared plus b squared. But what are a and b? Well, they're just distances. And a is a horizontal distance, b is a vertical distance. And this horizontal distance a can be found by taking the difference between these two distances. Now remember, the 3 and the 7 are nothing more than horizontal distances. They are distances from the y-axis. And so if we take this distance 7 and subtract this distance 3, we'll get this distance A. A is just the difference between those two horizontal distances. So that's all there is to it. So it's a 7 minus 3 idea. In a similar way, the y distance, the b distance, is a vertical distance, and it's nothing more than the difference between these y values. You see, it's the difference between those two. All right, and so to generalize the situation, this is a difference in x components, so we can call it x sub 2 minus x sub 1, and this is a difference in y sub 2 minus y sub 1. Notice the squaring of both of those differences. Okay, this is the distance formula. Now, in 3 space, we just extend this idea a little bit and use the distance formula that we have here twice. Here's how it goes. Suppose we want the distance from P to Q. Now, P and Q are associated with ordered triplets, and that's fine. We're not going to get into specific values for P and Q just yet. But the way that the distance idea is developed is like this, that P as a position, a point, resides on a plane which is parallel with the xy plane. Now the xy plane is sort of the flat surface that's right here. But P may have a z value associated with it that's not 0. It might be down, might be up from this xy plane. All right, if it's down, then the plane I'm talking about is parallel with the xy plane, and it's down at the level of wherever P is. If z is -2, it would take the xy plane and drop it down, boom, boom, 1, 2. And you have a plane parallel with the xy plane which contains P. All right. Now, and I'm doing this, I'm kind of thinking of it like this for a particular purpose, because I want to take that plane and I want to find a point on that plane called R. And I want that point R to be a place on this xy plane that I just described, which is directly below Q. Directly below. That is, I'm going to cause a perpendicular situation to occur between QR and RP. I want that to be the angle between those two to be perpendicular. Now, it doesn't look like it here, but remember, we're in perspective, and right angles just don't look like right angles in this situation. All right, so I want to calculate this distance P to R, and R is situated such that I described it a moment ago. Now, to describe the triangulation involved in the distance formula from P to R, I mean, it could be something. I have a lot of trouble drawing these things, but it might be something just this bizarre. And the right angle might be right in here. You see, that might be the position of the right angle. Even though it doesn't look like it, that might be it, because PR is the hypotenuse of some right triangle, you see, because we want the distance from P to R. Now, that distance, as we calculate it using our distance formula over here, is the square root of a squared plus b squared. You see, which is what we talked about before. I don't know if you can see this very well, but you can see it right here. PR as a distance is the square root of a squared plus b squared. Now, PQ, now you see we're using this PR distance, and we're using this segment as a right triangle, because remember I said that we were situating R so that it's directly below the Q, so that the triangle PQR is a right triangle, and the right angle is right here. And again, you can't see it. You can't tell that it's a right angle, but it's a right angle right there. And because this R is coming out at us, it's way out here closer to the camera. At any rate, because we have a right triangle here, we can use the ideas that we talked about before about developing the distance notion. And it is that this distance, now I'm going to call this distance from Q to R, let's just call it C for the time being. And so within this right triangle, we want the hypotenuse. So this hypotenuse, which is the distance PQ, is equal to this side squared plus that side squared. So PQ squared is equal to this side squared plus that side squared. Or PQ is the square root of PR squared plus C squared. But PR squared is A squared plus B squared. And it's the square root of A squared plus B squared. Now, the square root of this business squared, this squaring takes out the square root, so we have, for the distance from P to Q, is the square root of A squared plus B squared plus C squared. Now, what are A, B, and C? Well, A is a difference in X components. You see, it's just a difference of X values, just like the A that we talked about before. B is a difference in Y values. C is a difference in Z values. And that's all there is to it. That's all there is to it. There's a lot to it, but that's all there is to it. It's just a direct extension of what we've had before. So our distance formula then in a three-dimensional situation is this. Now notice it's just here's our old distance formula, and we just extend it with the difference in Z value squared for the distance formula in 3-space. All right, suppose we want to find the distance between these 2 points. All we do is pop in information. Now generally when you use a formula like this, you want to write it down first, and you could write it down like this. I've taken a little shortcut here because we are accustomed to thinking about delta x as being a difference in x values, and delta y as a difference in y values, and delta z as a difference in z values. Usually when we use this delta notation, we're talking about little tiny differences, but it doesn't make any difference. We can talk about some pretty big differences here. So the difference in x components, well, let's see, it's the difference between the 1 and the 2. So I'm using 2 minus 1. And then for the difference in y's, 4 minus 0. And the difference in z's, negative 3 minus 2. You see, and all of those differences are squared. So I've collected in these parentheses, and I get these values squaring and collecting. I find the distance to be the square root of 42. We could approximate it using the calculator, but that's old hat. We know how to do that. Now, another idea that we talked about in a traditional coordinate plane is the notion of midpoint. Now, the midpoint between, now here's our xy plane. The midpoint between these two, the point right here, does it make some sense that if we're going to assign an xy pair to this, and that's what we intend to do, that this distance is simply the average of this one and this one? You see, we have a couple of horizontal distances associated with this point and that point, and if we take those horizontal distances, you see, add them and divide by 2. This is the point right in between. So if we take the average of these two, then we've got that. And in a similar way, the vertical distance, this distance is found by taking the midway point between these two. All right, so the idea, the concept is that for midpoint in our traditional coordinate plane is average horizontal distance, comma, this is coordinates of a point now, average horizontal distance for the x coordinate and average vertical distance for the y coordinate. And the average is found by taking the sum of the x values and dividing by 2. You remember, average means that you add up a bunch of things and you divide by the number of things that you're adding. So here we're adding 2 things and we divide by 2. Here we're adding the y components and divide by 2. That's all there is to it. Now in 3 space it's a similar idea. It's an extension of that idea actually. And the midpoint between 2 points in 3 space is found by taking the average x distance, you see, average y distance, average z distance for our ordered triplet. So it's add the x's, divide by 2, add the y's, divide by 2, add the z's, divide by 2. Now, let's go through a problem. And in fact, let's slide over here and let's do this. Let's find the midpoint between these two. You see, and to do it, all we do is apply our formula. And the general idea, the general concept involved in it is the way that you'll recall it. The general concept. And what is that general concept? Well, the midpoint is an ordered triplet, and it is the average x value in these two, and I can put average x value, average y value, average z value, or I can just say x sub 1 plus x sub 2 over 2, average y value, y sub 1 plus y sub 2 over 2, and average z, that's z sub 1 plus z sub 2 over 2. And let's just plug and play. All right, add the x's, that's 1 and 2 over 2. Add the y's, 0 and 4 over 2. Add the z's, 2 and negative 3. 2 plus negative 3 means 2 minus 3 over 2. Let's see, 1 and 2, that's 3. 3 over 2, that's 1.5. Then 4 over 2 is 2. And 2 with negative 3 is negative 1, that's negative 1/2. So here then are the coordinates of the midpoint between those 2 points. From time to time, we'll be talking about a variety of 3-dimensional figures. The first one we'll talk about here is the sphere, and we'll talk about the equation associated with a sphere, and it comes from the equation associated with a circle. Now remember that when the circles were developed and the equations for circles were developed, they were developed in terms of the distance formula. If we have a circle whose center is at 4, 3 and it has a particular radius, then you use the distance formula by thinking of the distance r, and the distance is between the center of the circle and a general point xy that is on the circle itself. The distance formula is this, and that distance is the distance r that we're talking about here. A difference in x's is the general x on the circle minus the x component for the center. And then the difference in y is the y coordinate on the circle and the y coordinate at the center. And then using this, we square on both sides to clear the radical, and we have r squared is equal to this plus this. And to generalize the thing further, this situation further, if we're thinking about a center at a general point hk, then we have an h here and a k here. So the center is at hk and the radius is r. This is the equation of a circle. Okay, now we just extend the idea for the equation for a sphere, and we extend it just utilizing another point in the process into this other dimension, into this z dimension. So it's the distance is equal to, and we start with that distance formula, and then that evolves into a situation where we have an r squared here. The squaring clears the radical once again, and it's x minus h, y minus k, z minus l. And the center of the sphere is at hkl. You see, that's the idea, and the radius is r. Well, let's work a few problems. Suppose we have a sphere and the center is located at 2, 4, 3. The radius is 3, and we want to write the equation in standard form. Now, the equation can take a lot of forms, but the standard form is the form that we just looked at. So we might begin with the skeleton of the equation in standard form and just fill in the information we know. And we know just about everything here. We have the HKL is up here, so H is replaced with 2, and K is replaced with 4, and L is replaced with 3. The radius is 3, so r is replaced with 3, and we would presumably, though, probably write this as the 3 squared as 9, and this is the equation that we're looking for. Now, another question associated with this might be, does the sphere intersect the xy plane? Does this sphere, described here with this equation, intersect the xy plane? Now, we have to think about its location, and gee, if it intersects the xy plane, how can we determine that? Well, we might do that by thinking about the position of the center of the sphere, and where is that center located in relationship to the xy plane. Now remember, the x component of the ordered triplet can be thought of as the distance from the yz plane, the y component, the distance from the xz plane, and the z component, the distance from the xy plane. And that's the way we want to think about it here. So in this description of the center, we have a z value of 3. And if we were thinking about our coordinate, well, these coordinates and then we would be thinking that, gee, the first two items, the 2 and the 4, are describing distances that are x and y. They are distances we can think of as in the xy plane. That xy plane is this flat surface here that's coming out at you. Okay, think of it that way. And the z component gives us an up and down distance. So the z value is 3. So once we locate the xy business, the 2, 4, then we just go straight up from there, 3. So we go up 3. It's up 3 from the xy plane. That's how we can think about that z. And I'm probably overemphasizing this, but I'm doing it for a purpose, because when we're talking about a position that is 3 units from the xy plane, and we have a radius of our sphere of 3, then, gee, yes, if the radius is 3, and it's only 3 units above the xy plane, then there is one point, you see, where this sphere touches the xy plane. Consider this problem. Suppose we want to find the equation of the sphere if the points, this point and this point, are end points of a diameter. So these are the endpoints of a diameter, and we'd like to write the equation. How can we do that? Well, gee, a diameter, though, goes through the center. And so if we can find the midpoint between these endpoints of the diameter, then we'll have the coordinates for the center. Now, what about the radius? Well, a strategy for finding radius is to take the coordinates for the center and the coordinates for either of those two endpoints and just find the distance between those. Okay, let's do that. Now, we need to keep things organized, so we might label like this. We might say, okay, let's calculate the coordinates for the center. Now, the center would be the midpoint between these 2 points. And remember, midpoint is the average of the x's, average of the y's, average of the z's, or it's x sub 1 plus x sub 2 over 2, y sub 1 plus y sub 2 over 2, z plus z over 2. All right, and just plug in the values, and we find the coordinates of the center to be 1, 1, 4. All right, now we know where the center is. Now, what about the radius? Well, we can find that radius distance by finding the distance between this point and either of the other two. Now, we could also find it by taking the distance between those two and dividing it in half. That would be okay as well. But let's go directly at it. Let's find the distance between this one and either of those two. All right, so for the radius, use the distance formula. Notice delta x squared plus delta y squared plus delta z squared, all under the radical. So now, difference in x components. Well, I'm using the first given point over here. The first coordinate was 3, and the coordinate for the center, the x-coordinate for the center, was 1. So 3 minus 1. And then from over there, negative 2, and then minus the 1. And then the 6 was the y-coordinate of that given point, and then minus the 4, the y-coordinate for the center. And then performing the calculations, we find the r value, the radius, to be the square root of 17. And now all we do is put all of this together into the equation format. Here's the form of the equation. Now the HKL, those are the coordinates for the center, and those coordinates were 1, 1, 4. Now notice that those numbers follow minus signs here. That was an important consideration when we were talking about circles in earlier studies. But at any rate, so we have this part on the left, and then the r squared means the square root of 17 squared. But when we square the square root of 17, we get 17. And we would probably write this as 17 on the right. So here then is the equation we're looking for. Here's a problem where we have an equation which is in an expanded form. We might say that this is a general form of the equation for a sphere, and we'd like the standard form. We'd like a form from which we can gather information about the position of the center and also the length of the radius. Now, to place an equation from the general form into the standard form, we have to rewrite, and we're going to use the method of completing the square to write the little binomials which are squared. We've seen that process a number of times before. To begin, though, we just rewrite the expression in general form and put the terms involving x next to one another. So I'm writing this x squared and this minus 2x next to one another and leaving a space. And then the y squared next to the 4y and leave a space. And then z squared next to minus 6z and leave a space. And I kick the existing constant to the other side. The method of completing the square is one where we're sort of reinventing a constant, or we are inventing a constant that goes in this position so that we can factor into a binomial squared, binomial times itself. So we are completing the binomial square. Or excuse me, we're completing the trinomial square, and we are then, by factoring, identifying the binomial, which when squared gives that trinomial square. So that's the idea. At any rate, we're thinking of the terms involving x in this way, the terms involving y in this way, and the terms involving z in this way. So let's go through the process. Remember, it's to complete the trinomial square, it's half of this term squared. So half of the negative 2 is negative 1, squared is 1. So we're going to add 1 in the parenthesis. Now, by adding 1 here, though, we're causing an imbalance in the equation. To keep the equation balanced, if we add 1 on the left side, we have to march over and add 1 on the right. So we come over here and add 1. And then back over here, Now I can take this to the next step, and we can see that the factorization is x minus 1 squared. But we slide over, and let's see, to complete the square, half of 4 is 2, 2 squared is 4, so I'll add 4 in parentheses. And if I add 4 over here, I have to add 4 over there, so I go over here and I add 4. And then back over here. Now the factored form is y plus 2 all squared. And then for the terms involving z, to complete the square, half of negative 6 is negative 3, squared is 9. So I'm adding 9, but if I add 9 here, I have to add 9 on the right. And then back over here, factoring, I get z minus 3 squared. Now on the right, I'll collect the terms and find that my constant becomes 6. And now I can identify all of the components for the sphere. I know that the center is at an h, k, and l, and those are values that follow minus signs, and the number that follows a minus sign here is 1, and the number that follows a minus sign here, we have to think of this a little bit differently. We have to think of this as y minus negative 2. You see, in order to identify the number that follows the minus sign. That's a very important little nuance involved in this process. So this gives us a negative 2, and this gives us a 3, the number that follows the minus sign. For the radius, we need to identify the number which is squared to give 6, and so we would probably write this as the square root of 6 squared. And so we are identifying the radius then as the square root of 6. To set up the next problem, imagine that I have a basketball. Imagine that I'm holding a basketball, and I take this basketball and I lower it into a tub of water. And let's say that I just kind of push it a little bit into the tub of water to where it's just, maybe 1/4 submerged or something like that. Now imagine where, as the water meets the sphere, as the water meets the basketball, what kind of figure is formed? The intersection of the water with the basketball right at the surface of the water. You see, it's just a circle. It's just a circular path for the water. And that's what we're talking about in the next problem. And that path is called the trace. Now, we're thinking here about finding a trace in a particular plane associated with the graph of this sphere. Now, this sphere has a center at 3, 2, negative 4 identified here, and a radius of 5. And we want the xy trace. Now, that's the trace, sort of the intersection then of the sphere with the xy plane. That's what the xy trace is. And it's going to form a circle. So what's going to emerge here will be the equation for a circle for that xy trace. And all we do to identify a trace is to understand that for all of the values, the coordinates of points that lie on the xy plane, what are the characteristics of the coordinates of those points? Well, every one of those points that lies on the xy plane would have a z component, a z coordinate of 0. So the distance from the xy plane is 0 if we're on the xy plane. That's the idea. So the z value is 0. So all we have to do is take the equation up here and replace the z with 0. You see, and evaluate. Now that just causes us to change the value of the constant over here, and the z term goes out. But we have 0 plus 4, 4 squared is 16. If I subtract 16 on both sides, I get 9 for the constant on the right. And these components stay the same. So the trace is a circle, and here is its equation. And the circle has a center at 3, 2, and it has a radius of 3. And we could think about the xz trace, the trace or the sort of the imprint that this graph would make, this sphere would make in the xz plane. You see the intersection of those two. Now think about that. In the xz plane, the y value would be 0. So all we would have to do is replace y with 0 and evaluate in a way that is similar to this one.